Hypothalamus artificial intelligence, HI. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents the short conference, an autonomous mathematical language for cognitive robots. It corresponds to one of several short conferences, in which the advances of HI research are presented, on the topic of artificial brains and decision-making artificial intelligence. Conference prepared and edited by Jesus Velasquez Bermudez. His resume may be found on LinkedIn. Math the only language shared by all humans. And by cognitive robots. Charles Darwin said, "Mathematics seems to endow one with something like a new sense. Perhaps, structured mathematics may be the way to provide robots with the ability to communicate autonomously with each other." Language is related to many cognitive functions such as attention, orientation, communication, and memory. Language skills are not located in a specific brain area but in many of them. Traditionally, Broca's area, located in the left frontal lobe, and Wernicke's area, in the left parietal lobe, had been attributed to the production and processing of language, but today scientists know that many more regions are involved. We must abandon the idea that there is a brain area that is responsible of this. Broca's area was discovered in 1861 by French surgeon Paul Broca, who found that it serves a vital role in the generation of articulate speech. Our ability to articulate ideas, as well as use words accurately in spoken and written language, has been attributed to this crucial area. Wernicke's area serves for language comprehension, and the exchange of information between these areas, as in reading aloud, is done through the arcuate fasciculus. Some elements of the brain related to the language. Language is considered the engine of human evolution. It allows communication, the transmission of knowledge and the development of society. Human language, unlike animal communication, is symbolic, complex and adaptable, which has allowed humanity to reach a high level of complexity and social organization. Language is much more than a communication tool. It is a fundamental cognitive ability. In the same direction, the evolution of artificial intelligence will undergo a total change, the day when cognitive robots, or algorithms, can communicate autonomously with each other. There are two alternatives. Getting artificial intelligence to build a universal language, and/or take from mathematics the fundamental elements for it. HI has chosen the second path. Artificial brain, a swarm of mathematical programming algorithms. If large-scale multi-level optimization methodologies, based on partitioning and decomposition of systems, are applied to obtain the smallest atom of a dynamic stochastic process, the number of algorithms generated could become countless. Then, the solution of a mathematical problem would be carried out by a swarm of algorithms that work autonomously and permanently to achieve the goal proposed by the decision maker. This approach is currently used in artificial intelligence to manage swarms of robots, but the rules that robots follow are simple, particular, logical, and intuitive, and do not have a universal mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a sparse multi-level matrix, and whose communication protocol is governed by formal mathematical laws, aimed at obtaining results as a team. Normalization and standardization, the base of a universal language. Muhammad ibn Musa al-Khwarizmi, mathematician and Arab astronomer, introduced European mathematicians into the Indo-Arabic numerals and in the fundamental principles of algebra. Algebra is the intellectual instrument which has been created for rendering clear the quantitative aspects of the world. The foundations of Optext database algebraic languages consider the algebra as a standard, to express the relationships between the different parts that make up a mathematical problem. It can be said that there is only a reduced way to write an algebraic equation. This is independent of the symbols that are used to represent the physical or logical relations. Additionally, if two algebraic formulas are joined, a new algebraic equation is obtained that retains the same structural characteristics of the original equations. This transitivity law may be extended to mathematical programming, MP, which in essence is a collection of algebraic elements. The foundations of Optext database algebraic languages consider the algebra as a standard, to express the relationships between the different parts that make up a mathematical problem. It can be said that there is only a reduced way to write an algebraic equation. This is independent of the symbols that are used to represent the physical or logical relations. Additionally, if two algebraic formulas are joined, a new algebraic equation is obtained that retains the same structural characteristics of the original equations. This transitivity law may be extended to mathematical programming, MP, which in essence is a collection of algebraic elements. Then it is possible to join two MP problems to obtain a new MP problem. It is also possible to divide an MP problem into two MP problems. Resuming, if the formulation of algebraic expressions is normalized, it is possible to have a standard way of representing a mathematical model that can be understood by another mathematical modeler, making it a standard for formulating MP problems. Additionally, the combination, or division, of MP problems generates new MP problems, which can be solved using many optimization technologies. Therefore, to facilitate the development of models, it is convenient to establish basic principles, norms or standards, of modeling, in order to enhance the use of models and ensure that they remain current over time, thanks to conceiving as a dynamic structure that adapts to changes in computer technologies. This implies, previously to the implementation of mathematical models, establishing a standardization manual that guarantees the understanding of the mathematical model, by any professional knowledgeable about the subject. This fact will result in the portability of mathematical models and the significant decrease in the implementation time. Duality theory. Joseph Louis Lagrange was an Italian mathematician and astronomer, later naturalized French. In mathematical optimization, the method of Lagrange multipliers is a strategy for finding the local maxima and minima of a function subject to equality constraints. Using the implicit function theorem, the seminal Lagrange idea is to convert a constrained problem into a form such that the theory of an unconstrained problem can still be applied. Here resides the foundations of constrained optimization and duality theory. In mathematical optimization theory, duality or the duality principle is the principle that optimization problems may be viewed from either of two perspectives, the primal problem or the dual problem. If the primal is a minimization problem, then the dual is a maximization problem, and vice versa. Any feasible solution to the primal, minimization, problem is at least as large as any feasible solution to the dual, maximization, problem. Therefore, the solution to the primal is an upper bound to the solution of the dual, and the solution of the dual is a lower bound to the solution of the primal. This fact is called weak duality. In general, the optimal values of the primal and dual problems need not be equal. Their difference is called the duality gap. For convex optimization problems, the duality gap is zero under a constraint qualification condition. This fact is called strong duality. According to George Dantzig, the duality theorem for linear optimization was conjectured by John von Neumann, immediately after Dantzig presented the linear programming problem. Von Neumann noted that he was using information from his game theory, and conjectured that two-person zero-sum matrix game was equivalent to linear programming. Rigorous proofs were first published in 1948 by Albert W. Tucker and his group. Dantzig's foreword to Nuring and Tucker, 1993. Duality theory is involved in virtually all algorithms that solve the problem using mathematical principles. Example: robots speaking using Bender's theory. In 1962, the Dutch mathematician Jacques Benders publishes his theory of partition that is a transcendental step, not the first, in parallel computing, aimed at solving complex mathematical problems, dividing them into more elementary subproblems. The solution of an optimization problem using large-scale optimization methodologies, LSO, is based on partitioning the problem into two subproblems, algorithms or cognitive robots, that must be solved in coordination. The most used techniques are two. In Bender's theory, BT, the partition is performed according to the variable's type, and in Lagrangian relaxation, LR, according to the constraints type. BT is a primal technique, primal feasible, meets feasibility conditions, also known as outer linearization, or decomposition by quantity/resources. In BT, variables are called coupling, or control, variables and the remaining dependent, or coordinated, Variables. The hierarchical relationship implies that at the top level the coordinating robot on control variables operates and at the lower level the slave problem about coordinated variables is solved. This problem is parameterized as a function of control variables. In response, the primary level returns information to the coordinator focused on the value of the dual variables of its constraints. In its basic form, BT is applicable directly when subproblems are linear. LR is a dual technique, dual feasible, meets optimality conditions, also known as interlinearization, or decomposition by prices. In LR, the primary level returns information to the coordinator focused on the value of the primal variables, and received information about dual variables. Bender's partition, or Bender's decomposition, is a technique in mathematical programming that allows the solution of very large mixed linear programming problems that have a special block structure. Bender's conceived the solution to the optimization problem as a communication between a coordinating problem and a subordinate problem. The coordinator problem sends signals to the subordinate problem, which corresponds to the optimal primal solution of the coordinator. With such information, the subordinate problem solves a problem parameterized in the value of the primal variables of the coordinator, and sends signals to the coordinator, which correspond to the dual variables of the subproblem. The coordinator incorporates the information of the subproblem, in the form of cutting planes of its primal feasible zone, and performs a new iteration, to send primal variables to the subproblem, to continue the iterative process. The importance of Bender's theory, which followed the work of Dantzig-Wolff, is that it resulted in parallel optimization, based on the theory of duality. But it can also be understood as the conversation between problems, or algorithms, or robots, to solve a problem as a team with a common goal. The communication protocol is the rules established by Bender's. The Bender's approach allows any pair of related systems to split and communicate with each other, to jointly solve a related problem. It is also possible to divide an MP problem into two MP problems. When considered the algebraic formulation, it must be considered that for its union, coupling constraints and coupling variables are required, which guarantees the matrix structure specified by Bender's, which must be of the dual angular type. Based on the concepts of partitioning and decomposition, it is possible to decouple a system, to obtain vertical structures partially similar like of the human neocortex. The principles of transitivity between MP models, formulated based on a database algebraic language, can be extended to more complex structures, such as those derived from the partitioning and decomposition of systems to apply large-scale optimization methodologies. In this way, the new vision of mathematical programming involves defining the relationships between problems, as the next step after the definition of the equations that compose them. Bender's theory can also be used to establish communication between mathematical artificial neurons, concept created by Jesus Velasquez, to build artificial brains. The mathematical artificial neuron is a mathematical model, presumably of optimization, which results from the partitioning and decomposition of a monolithic problem into an atomized model, following the mathematical laws of large-scale mathematical modeling. Two mathematical artificial neurons communicate with each other, forming a network of mathematical artificial neurons. Communication occurs in two directions between the two neurons. The communication protocol between the two neurons is defined by mathematical laws developed to solve atomized problems. The modeler can choose the protocol, but not the communication process, which for optimization is based on the scientific laws of duality theory, and for equilibrium problems in mathematical programming with equilibrium constraints, PEC, methodologies. The information flow shown corresponds to the standard Bender's methodology. Linear subproblems. The information flow shown corresponds to the extended Bender's methodology, developed by Geoffrin. Nonlinear subproblems. The information flow shown corresponds to the extended Bender's methodology, developed by Geoffrin. Nonlinear subproblems. The union of large-scale technologies with parallel computing is increasing every day. The image indicates that a complex optimization problem, which can be solved in a unit of time, say an hour, using simple sequential methodologies, could take 400 hours, 16.66 days. If the appropriate technologies are not available, an unsuspecting professional would conclude that the problem cannot be solved in a reasonable time. Artificial hippocampus, storing history of runs. The learning process of the human being is concretized in memory, which accumulates information, data already processed, to face each new situation, using the knowledge stored that has been made up to that moment. This knowledge is stored in the hippocampus where the data is organized according to its age. Like any physical element, its use affects its reliability, and that is why short memory, the one that stores the data of the last moments, begins to fail with age, until it is lost, while long-term memory can store very sharp data, but that require greater access time to locate them. This section describes the structure and functioning of an artificial hippocampus for advanced mathematical modeling, taking as a reference the basic structure of the human hippocampus, and its incorporation as part of an artificial brain. The artificial hippocampus is an expert system that must store two types of knowledge. Formulation: the components of mathematical models, and historical data of the results generated solving the mathematical problems, using large-scale optimization methodologies. This historical data may be used as starting point in future uses of mathematical models to support decision-making. Production and storing of data, primal and dual variables, are analyzed using Bender's theory. This methodology can be extended to many other cyclical processes to solve problems. In a very simplistic way, it could be said that the hippocampus stores information to support human decision-making, using two strategies. Guide the humans to achieve the goals that give you pleasure, well-being. Protect the human being from what he does not want, or should not, or cannot, succeed him, because of the consequences that may entail. While mathematical models on digital computers, and the data storage disks, date back many years, more than 60 years, and despite the Industrial Revolution 4.0, how to run a model, it does not seem to have evolved. The normal process is: the model is thinking monolithically. A high-performance solver is selected to solve the problem, and the results are post-processed, and the results of the models are stored, with administrative purposes. Usually, in the next run, the model starts from scratch, ignoring the past, that is, it has no memory. In some cases, it is heated from a starting point provided by the last run, presumably the last optimal solution, or a point that ensures feasibility. However, an artificial hippocampus, designed for the artificial brain, can take advantage of a lot of information produced within a run, and during the history of all runs. Two examples will be briefly presented: handling of Bender's theory, and generation of convex hull. In large-scale optimization methodologies, the information produced by the algorithms, during the process of solving the problem, is focused on the primal and dual variables resulting from the parametric solution of the problem for different hypothetical situations, in such a way that potential solutions are predicted to form an approximate multidimensional surface of the objective function, using cutting planes, in the neighborhood of the optimal solution. The values of the objective function away from the optimal solution are ignored, in such a way as to lighten the load with respect to the processing of unnecessary information. The information produced is combined, through cutting planes, to determine two areas in which the system can and should be operated. This is concretized in eliminating decisions that are not convenient, because they are not optimal, and utopian decisions, because they cannot be achieved. Taking as a reference the Bender's theory, BT, the use of the models of an artificial hypothalamus can be conceived as a cyclical process in which several mathematical models, at least two, are dynamically solved. In each new run, the parameters of each mathematical model change, inputs, and therefore a re-optimization is required. Normally, the re-optimization process starts from scratch. The artificial hypothalamus is described below. The artificial hypothalamus is composed of a single mathematical model, the M model. The model is represented based on the BT that includes two mathematical problems. Coordinator, who is responsible for solving the integrated problem using cutting planes to control the feasibility zone of its variables, and slave, who is responsible for producing the data required by the coordinator to generate the cutting planes that synthesize the relationship between the coordinator's variables with the slave's variables. The end run of the M model implies an interactive cyclical process, in which multiple times the coordinator and the slave are solved, establishing a conversation between the two problems, and the optimization process begins from a starting point. The conversation between the two problems is based on a protocol that can be synthesized into. After solving a mathematical problem, the corresponding algorithm stores in a database the dual and the primal variables obtained, and before solving a mathematical problem, the corresponding algorithm read from the database the last value of dual variables and of primal variables produced for the other problem. This information is incorporated into the receiving problem according to BT. The knowledge database that is assembled, in step V, contains the entire series of values of dual variables and of primal variables, that are generated throughout the process. The activities to be carried out for the M model in each N cycle can be summarized as: read sets and parameters for N problem, read weighted information of runs, 1, 2, N, optimize N problem, store information of N run, and follow to the next iteration. All the above activities are trivial except for activity 2, read weighted information of runs, which represents, from a mathematical point of view, the management of long and short memories of the artificial brain. This process can be called memory management, MM, and is fundamental in the artificial hippocampus since it has the functions of an inference engine in an S. For each model M in each cycle N in each iteration K, must store the values of the dual variables, the primal variables, and the extreme rays of the feasibility zones. From this information it is possible to construct the cutting planes of past problems and potential future problems. Additionally, may be included variables, such as the dual variables of the cutting planes, which can be used to enrich the inference engine of the artificial hippocampus. The process of populating the knowledge database can be conceived as the sum of two processes. Knowledge accumulation that exists in the multiple solutions of problems, and knowledge generation during the idle time of the computers, pre-solving the complex part of a large complex mathematical models, replacing optimal convex, or non-convex, hull that synthesize the optimal behavior of parts, subsystems, of a complex system. Following the principles developed by Benders, it is possible to build an artificial hippocampus that remain active and useful beyond the duration of a run of a computer model. To do this, the cuts generated in each run must be stored in such a way as that they may be used later. This implies a coordination work, since it cannot be guaranteed that the information as it is produced can be reprocessed later. This can happen at any time. An artificial hippocampus stores cuts from one run to be used in the next, which will produce new cuts. Hai is researching in the creation of methodologies to generate new rules that fit the dynamic variation of the parameters that affect the models. The process is similar for Lagrangian relaxation. Another alternative to generate knowledge, that is stored in the artificial hippocampus, is the generation of convex hulls, associated with optimal solutions of the mathematical problems. The multidimensional grid that represent the convex hull can be incorporated into the integrated problems, to accelerate the solution process. Depending on the specific problem, the convex hulls may be permanent, or they must be recalculated dynamically when the parameters of the mathematical models change. The example describes the extraction of the model of the pumping stations, from a pipe model, to replace them with convex hulls that represent the optimal behavior of each pumping station, then a mathematical grid model that represents the optimal operation of the pumping stations must be inserted. This will speed up the execution of the model. Management the memory. A generalized rule of human brain behavior is when solving problems, people use their long-term, permanent, memory that they apply to current situations, contained in their short-term, transient, memory. This should be no different in an artificial brain. If when start to solve the problem of event N data stored in memory is used, it is necessary to define how to manage math memories. This process was not studied by Benders, and, in general, it has been little studied. At least two problems should be studied. What part of the memory to use in the warm start process, and how to do it? And How far must grow the amount of data stored in memory? For these problems there does not seem to be an exact math solution. It is necessary to design an empirical, heuristic, solution that is based on a mix of the mathematical laws and the logic of the process, perhaps as humans do. Another possibility is to use artificial intelligence tools, like artificial neural nets, that link behavior patterns of the dual variables with behavior patterns of the parameters. For example, a basic artificial hippocampus can be constructed using Bender's partition theory, which can be interpreted as: the general problem is divided into two complementary subproblems, an experimenter, that makes decisions in real, or in simulated, environments, and that send the results to the higher level, and an information manager, that stores the results, sent as primal and dual variables. When it is required to make a real decision, or to perform an experiment, the information manager processes the stored data to determine two zones with respect to decisions, a desirable zone and a non-desirable, or utopian, zone. Mathematically, this is done by generating cutting planes and incorporating them as part of the information to be processed. The experimenter receives the information from the manager, makes decisions, and sends the results to the manager. The speed with which this loop is made can be that of an algorithm that does not stop until it finds the optimal solution, or that of a human who makes decisions step by step. The first non-optimal zone that contain values of the decision variables that must be discarded because they cannot be optimum. From a human point of view, it contains decisions that should not be taken because there are better. The second non-feasible zone that contains values of the decision variables that must be discarded because they cannot be feasible. From a human point of view, it contains decisions that cannot be taken because they are impossible. Decisions not included in the two zones determine the area of rationally desirable and possible decisions. As the learning process progresses, the convenient area is reduced, in such a way that many decisions seem intuitive. If memory does not fail, the humans will remember in each new decision-making process the story, and their decisions will be faster and more successful, and they will learn from each decision made. Autonomous real-time robots communication. The central part of an artificial hypothalamus is the formalization and the standardization of a math language between cognitive robots, to be used as the way to communicate multiples math algorithms. The core of this language is the duality theory, that support the mathematical programming algorithms, that may be developed using the concepts of large-scale optimization methodologies, to solve high complex math models based on the partition and the decomposition of the real-life complex systems. An artificial hypothalamus corresponds to a superalgorithm that coordinate multiple cognitive robots that operating simultaneously, autonomously, in real time, acting as the human hypothalamus, to achieve a common goal. By joining all the concepts presented here, it is possible to define a language between robots, math problems, algorithms, or agents, based on an exchange protocol of information between the multiple types of problems, in which any pair of robots communicate by exchanging the information produced by each of them, which is synthesized in the value of the primal and the dual variables that they produce. If each robot is identified by the R index, in each conversation step K, the actions of each robot are inputs, dual and primal variables that our robot uses produced by other robots. All the data available until the begin of conversation step K is characterized as the historic knowledge database QK. Outputs, primal and dual variables that produce the robot R, it can be characterized as XKR, PKR. Transformation function FRQK, mathematical problem that the R robot solves to produce XKR, PKR, starting with QK. Mathematically this is XKR, PKR, equals FRQK. QK equals QK minus 1 union with XKR, PKR, Q0 equals. When our robot receives information QK, it processes it generating information, XKR, PKR, and a conversation step K plus 1. The robots receive, or search, the inputs produced by other robots, and produce the outputs to be used for other robots. The information produced is added to the historical, and it is stored in the artificial hippocampus, an intelligent database on disk, or in RAM, which can be accessed in the next conversation of all robots. Then, based on large-scale optimization methodologies, communication between robots is synthesized in the transformation functions FRQK and in the storage of all the information produced, XKR, PKR, in an optimization knowledge database, QK, which can reside on RAM disk, offline, or on RAM memory, online. In a static problem, frontier conditions fixed, when the coordinator robot detects that has enough information to establish the optimal decision, it proceeds to close the conversation cycle, and terminates the optimization process. If the problem is dynamic, frontier conditions time-dependent, the robots will have a continuous conversation in order to keep the system as close as possible to the optimal decision path, which is not possible to obtain due to system uncertainty. This process, based on duality theory, is the support of artificial hypothalamus capable of processing the information required for Industry 4.0. Communication between robots, using a universal mathematical language, is a fundamental step for a community of robots to act autonomously, through an artificial brain, based on parallel and distributed optimization processes. Parallel, because they optimize atomized problems through parallel mathematics, and distributed, because they move to mix multiple optimization models, representing different agents of the system. Alice, which way I ought to go? The Cheshire Cat. It doesn't much matter which way you go, if only you walk long enough. Thank you for your attention.